Hey, hi everyone, and welcome to our webinar series again. And welcome, Jose. Hi, thank you for being here and thank you for accepting to give a talk in our series. And so, yeah, okay. Today's speaker is José Morillas. He's a postdoc at Universidad de Granada. And I miss you, Jose. Jose was my my colleague. We were in the same office while being here in at City College at Levitt Institute in New York. And so before starting your talk, Jose, can you quickly give us a brief summary of your career? What did you do? Where did you do your studies? And what are you doing now? And what do you aim to do?
Yeah, it's very easy. My history is very easy. I I got my degree in physics here at the University of Granada. Then I did my master in physics again at the University of Granada again. And then I got a postdoc position there at the City College. I was in the City College for 2 years till the last September. And well, my postdoc consists in 3 years, two abroad and 1 year back here in Granada again. So now I'm enjoying my last year of that contract at the University of Granada. And in all of the phases, let's say degree, master, PhD, and so on, I've been studying magnetorheological fluids under different configuration, different fields, or different formulations. So I guess that my future is closely related to Magnetorheology. Well, let's see if I can discover something really interesting.
And you're looking for a position in Granada again, right?
Exactly. I want
Okay.
to get some stable job inside University of
In
Granada.
academia, okay, yeah, in academia,
Uh,
just to be clear, okay.
yeah, yeah, sure.
And while you were here in New York, you had a Marie Curie fellowship, right?
That's right. Yeah, that's the postdoc. Well, I think that if you, at least if you want to have a good future in academia here in Spain, you need to go abroad at least for 2 years. Otherwise, you will have a lot of problems later if you want to promote inside the university. So, well, I think that I chose the City College because of Jeff Morris. I read his book on microhydrodynamics or what, rheology of suspensions, and I was shocked because it was the first time that I think I really understand about suspensions of rheology of suspensions. I asked him if he wants to be my supervisor. He accepted. Luckily, I got the that fellowship. That's all.
And so how did you get this Marie Curie fellowship and like I don't know, how did you look into postdocs and what was the process to get here to New York?
Okay, so I will say that in order to to success in research, you always have to aim, sorry, to the best things you can afford. So although you are going to fail, I think that's not important. You have to try it because if you are lucky or you really deserve it, you can want it, and that's make easier in the future. So I think Marie Curie are the most important fellowships in terms of postdocs at European level. Well, indeed, for a Marie Curie, everybody can apply. You don't have to be European. You can be from anywhere in the world. Because that was the best one. I tried it. I applied for it. Of course, I applied to other fellowships as well, just as Plan B, Plan C, and all that stuff. But well, it resulted that I won that fellowship, enjoying it.
So you hear it, people. Just go ahead and try the best you can find.
Yeah. Yeah.
Okay, then let's start the talk, unless people have some questions directly for you. And in general, people, if you have questions, just raise your hand. You have the button here in Zoom or write into the chat. And I'm sure Jose would be glad to answer live the questions. I think that's better. And so Jose, please go ahead and start sharing your screen. You should be able to just stop my screen sharing.
Okay.
Perfect.
Okay. So thank you, Leah. Thank you, Michelle, for inviting me to this webinar series, and thank you, everybody, for attending this one. Today, I will talk about magnetorheology, which is a research field with a quite a long history, but using a magnetic field configuration that has not been researched so much. They are the triaxial magnetic fields. This is the structure of the talk, but I will focus mainly, in first place, on the numerical modelization of MR fluids. I will show also some results relating microstructure and rheology. But I would like also to save some time to show our advances in the experimental setup we have developed in order to perform experiments under this kind of magnetic fields. So as probably you know, magnetorheological fluids are suspension of magnetizable microparticles in a common liquid that in the absence of a magnetic field, they behave as nearly hard sphere suspensions. However, when you apply an external magnetic field, each particle gets a magnetic moment, and in first approximation, that magnetic moment is a point dipole, which is proportional to the external magnetic field. So all the dipoles have the same magnitude, and all of them are aligned with the magnetic field. The interaction between dipoles is this one, so it is analytically known. It has two main properties. One is that it is a long-range interaction, and the other one is that it is anisotropic. So here in this plot, in this graph, I have plotted the force felt by a witness particle due to a source particle, which is at the origin. And you can see that the force is anisotropic. There exists a critical angle between the field direction and the interparticle vector, below which the interaction is attractive and repulsive for angles that are above that critical angle. So following this interaction, the typical particle arrangement are chain-like aggregates that follow the magnetic field direction. What is more, if you try to move apart the pair of particles that are aligned with the magnetic field, you try to move them, for example, shearing them, there is a restoring force that tries to keep the particle and move them back to the original position. So the aligned configuration with the magnetic field is a stable configuration. And that recovery force is the main responsible one for the two most known properties of MR fluids. Those are the Gilles stress and the shear thinning behavior. Both features have been studied for a long time using constant magnetic field. They are controllable by the magnitude of the field and the particle concentration. But in this talk, we will focus on a different field, which is a fast balanced triaxial magnetic field. Those fields have their three components changing in time, but fulfilling three requirements. The first one is that the three components have the same root mean square value. The root mean square is just the time average over the period of the component square. The second requirement is that the time average of the product between different components is going to be zero, and we will see later why this is important. And in this animation, you can see two examples of magnetic fields, of balanced triaxial magnetic fields. But any other configuration fulfilling those two requirements and the third one will return the same results. The last requirement is that the period of any of the components is going to be much shorter than the typical time for a particle to move under the action of the force in the liquid. So in that case, what particle feels is not the dipolar force, but a time average of the dipolar force. We will compute it later, but at this moment, I will highlight that it is a multiband interaction. That means we have a hand here.
Yes, just a really quick question before we can proceed. what is the nature of your particles? Are like, what are the size of them? Are they ferromagnetic? Are they paramagnetic? What exactly are they?
Yeah, well, they are magnetic. I think that paramagnetic or ferromagnetic is not very important if you work at a small magnetic fields. In the talk of today, we will work at a small magnetic field. So if it is ferromagnetic, it will be in the linear magnetic regime, and the size of the particles is microparticles, so above 1 micron, below 5 microns, in order to avoid sedimentation rate that is too fast.
Okay, thank you.
You're welcome. Okay, so yeah, it's a multi-body nature. And here, for example, we are plotting again the force that a witness particle feel due to a source particle when they are exposed to a balanced triaxial field. So you can see that now the force is central and it is attractive regardless the particle position. But if you now substitute the particle at the origin by a doublet, you can see that the force is not central anymore, and what is more important, you cannot compute this force knowing the solution of the two isolated particle problem. So thanks to this multi-body interaction, we can pass from the chain-like aggregates under a constant field to this isotropic gel-like structure. So our objective now will be to assess the rheology of these kind of structures numerically and experimentally. Regarding the simulations, we have implemented Brownian dynamics simulations, and as probably you know, this is the most simple flow chart for those kind of simulations. Once you know the position of the particles in the current step, you compute all the forces over each particle, and with that force, you update the particle position. In our simulations, however, we are going to go back a little and check the multi-body nature of the force because it is going to change the flow chart of this code. Instead of talking about the force, I will talk about the energy because it is easier to talk about a scalar quantity instead of the three components of the force. All the details, because here I will be fast, all the details you can find in the original references that are on top of the slide. So we start from the general expression for the energy between two dipoles that can be pointing in arbitrary direction and they don't have to share the direction. But if you assume, as we have done before, that all the dipoles are parallel to the external field, the energy simplifies to this short expression. So at this moment, we are going to save this term and we will put here on the right, just to keep it in mind, and we will go back later to it. Again, the magnetic field changes so fast, so we are not interested at the energy at each time of the simulation, but on the time average of the energy. So just imposing that all the dipoles are proportional to the external field and introducing the average inside the brackets, you obtain these two terms that you can develop in that way. Now we can use our second condition to be for a magnetic field to be balanced. The product of the different components goes to zero, and all those terms will disappear. So we can rearrange this expression in this way. So if you notice, now the energy is the sum of three terms, but those three terms are very similar to the energy under a steady magnetic field when it was applying only one direction. And this equation is telling us that the total energy under a balanced triaxial field, once it is time average, is the energy you will obtain by applying to the particle configuration a magnetic field in the x direction with a magnitude which is the root mean square value of the x component of your original field. Then you repeat the same, but now with the y component in the y direction, and the same for the z component in the z direction. So that is written here in a compact form. The energy, the time average energy is the sum of the energy of those three cases. And of course, that is not the same that applying the three components at the same time. So that's the point. And finally, we can apply the last requirement. The three root mean square values are the same. And if you do that, one obtains this surprising result, and it is that the time average of the energy is 0. Clearly, this is wrong, because if the energy is 0, there will not be any self-assembly under the triaxial magnetic field. The reason why this is 0 is because our first assumption imposing that all the dipoles are aligned with the external magnetic field. It's true that the dipoles are aligned to the total magnetic field, but the total magnetic field is not just external field. The total or local magnetic field at a particle position is the external field plus all the secondary magnetic field created by the surrounding particles. So in general, the local field at particle F is not going to be the same in magnitude or direction than the local field at particle S. And that's the reason why the solution of the two-particle problem cannot be used to solve the three-particle problem, because the local field in a problem with 3 particles is not the same that the local field at the particle position of the two-particle problem. Just before moving forward, 2 remarks about the local field computation. The first one is that the local or the magnetic field is also long range, so it is not enough including in this sum just contacting neighbors. You need to include particles that are far away. And the second point is that if you want to compute the local field at particle F, you will need to know the local field at the rest of the particles, but that quantities are still unknown for you. So you have to proceed with an iterative method. So assuming that all the local fields are the same and update the local field particle by particle, get a second solution. With the second solution, go into here again and obtain the third solution and so on till get convergence. Or the second option is realizing that this expression is indeed a linear system of equations, so you can get the inverse of the matrix and solve everything in one step. In any of the cases, solving it in following iterative methods or the direct method, the computation of the local field is the most expensive from a computational point of view. So knowing that, we can go back to our flow chart in the Brownian dynamic simulations. And now we have to include necessarily, before the computation of the force, the computation of the local field. And what is more, those 2 steps, field and force computation, you have to repeat it 3 times because the total force that you have to use to update the particle position is the force you will obtain when only applying the X component, only the Y component, and only the Z component. So implementing those simulations, we have included as well, in addition to the magnetic force, a repulsive force to avoid overlaps and the Stokes drag load. Using the typical scales for length, force, and time, one realized that the system is only driven by 2 dimensionless numbers. One is M, N, and D. B is the ratio between the repulsive and the magnetic force scale. In our simulations, is very large, just to avoid overlaps, so it hasn't any other role in the simulation. And the second dimensionless number is the Mason number, which is just the ratio between the shear forces and the magnetic forces. So giving values to those 2 parameters, you can update the particle position. And for each new configuration, we compute the shear stress as it is usually done. All the results I'm going to show here correspond to a Mason number of 10 to the minus 3 and a volume fraction of 10% in volume. And regarding the initial configuration, we allow the system to self-assembly before applying the shear flow, just to check to test the rheology of this structure. So with those simulations, we obtain this shear stress versus a strain curve. And that is completely different from the one that you will obtain under a steady magnetic field. So in the following, I will try to relate that change in the stress with the change in the microstructure. To do so, we have sort the particles according to their individual contribution to the total shear stress of the sample. So here we plot in green particles that do not contribute on average to the shear stress, and we plot in red and blue, respectively, the particles that contribute positively and negatively to the shear stress. And you can see that as the strain increases, more and more orange particles become green, and they finally form sheet-like aggregates that belong to the flow vorticity plane. In quantitative terms, those are the number of green particles and orange particles. And again, you can see that the decay in the stress is related to the increase of the number of green particles at the expense of the number of orange particles. So it seems that the sheet formation is behind the decrease in the shear stress. To check that, we have looked for a rule based on the structure of the suspension that allow us to sort the particles in sheets or not. And we have done that by coloring the particles according to the number of contact neighbors. And you can see that the majority of the particles in the sheets, they have 6, 5, or 4 neighbors. So we have proved that further by defining several order parameters depending on the number of neighbors. There's something in the chat. Probably okay. The question is why the curve of shear and strain is so noisy. Probably it's because I have just done, well, in that graph is the average of 3 independent runs. Maybe if we increase the number of runs, everything will go smoother. The problem is the computational cost that you have to use in order to get the full curve. Because indeed you have to simulate till a strain of 10 units, which is quite large in order to see the whole transient. Yeah, I would say that it is because we need more independent repetitions.
And also, maybe I missed that, but how many particles are those simulations?
1,000.
Okay, so maybe it's also that.
Okay.
I mean, 1,000, it's already enough. But... Okay.
Okay. So yeah, we have defined several order parameters depending on the number of neighbors. If you have 4 neighbors, we take as order parameter the distance between the 4th neighbor and the plane. In the 5 neighbors case, it is the angle between the plane and the line that joins 4th and 5th particle. And in the 6 neighbors case, it is the angle between the planes. And in this slide, you can see how the shear flow melts the original structure, plotted in black, and promotes a single peak at 0 distance for the 4 neighbors case and 0 angle for the 5 and 6 neighbors case. So pointing that particles with 4, 5, and 6 neighbors have all their neighbors in the same plane, or they are forming sheets. So we can go back to this slide, plot the number of particles with 4, 3, 5 neighbors, and so on. But we have just seen that particles with 4, 5, and 6 neighbors, they form sheets. So we can plot all of them together here, and you can see a good match between the number of particles that do not contribute to the shear stress and the number of particles in sheets. That behavior can be easily explained taking into account that the shear stress is proportional to the interparticle interparticle distance in the gradient flow direction. But if the pairs are in the sheets in the flow vorticity plane, that distance is going to be close to 0, so the shear stress is going to be at 0 as well. In the same way, we can merge together the rest of the particles with 2 or 3 neighbors, and because they are usually at the borders, at the rim of the sheets or close to their defects, we have called them defects, and again we obtain a good agreement between the number of particles contributing to the stress and the number of particles in the defects of the sheets. Anyway, you can also see that at the beginning of the straining process, sorting the particles in sheets or not is not a good idea to explain the initial increase of the shear stress. So in order to know what structures are promoting this steep increase, we have followed a different strategy. Now we compute the pair correlation function, but only between particles that contribute positively to the shear stress. So only between the orange and red particles in the movie. And here are the results. So this is the radial distribution function, and this is the pair distribution function, but in the flow gradient flow plane. And you can see that the majority of the particles contributing positively to the shear stress, they are forming pairs at contact, and they are basically aligned along the extension axis. That behavior is kept during the beginning of the straining process. Here we are plotting again the pair distribution function, but in a spherical surface with radius equal to the particle diameter. So it will be as this plot, but instead of in the ring, it will be in the whole surface of a sphere. And you can see that the probability is only high around 45 degrees and 235 degrees, so along the extension axis. So basically we have done another search, in this case looking for any particle that has at least one neighbor in this blue area, so along the extension axis plus uncertainty. Once we know those particles, once we have identified those particles, we know the individual shear stress, we can sum all of them and we obtain the blue curve. So the agreement is not perfect, but you can see at least that we can recover the steep increase in the shear stress, pointing that at the beginning of the straining process, the main contribution to the shear stress may come from particles that are at contact and tilt along the extension axis. If that's right, we can also predict analytically that behavior just analyzing one doublet. If you remember from the beginning of the simulation, from the presentation, the magnetic force in that case was central, so you can compute very easily how the deflection angle changed with time or with the strain. And once you know that, you can plug it in the definition of the shear stress, obtaining this functional dependency. If you plot it, you get those curves. The black one is assuming that at time zero, the particles are aligned in the y direction, and the red curve is assuming that any of the pair can have any orientation in the 3D space and averaging over all those possibilities. In any of the cases, you can see that the shape and the position of the maximum is quite close to or quite similar to the one we have seen in the simulations. So what we have done finally is to relax this expression, introducing two fitting parameters in order to fit the green curve. And well, at least we are still able to get the steep increase of the shear stress versus the strain. And well, with this, I finish the first part about the modelization of MR fluids under balanced triaxial fields, and now I will show the experimental setup we have developed in order to run experiments under those conditions. Basically, what we are looking here is for a generator of magnetic fields that can control the three components of the magnetic field independently, but also with a size or with a design able to fit in a rheometer. Our starting point is the plate geometry we are going to use. So our sample will have a cylindrical shape with dimensions that are close to those ones. The most controllable and accurate way of creating a magnetic field in a given direction is making a current flow through a coil, which is placed normal to that direction. And of course, for a fixed current, the larger the number of turns, the larger the magnetic field you can create. Because we want some homogeneity inside the sample, we will need to place symmetrically respect to the sample another coil where the current flows in the same sense as the original coil. And the main drawback of this configuration is the small magnetic field magnitude it can create. So what we are going to do is to wind the coils around a magnetic yoke. So basically we are designing an electromagnet. The key point here is the material you use for the for the yokes, because you need to guarantee that there is not any phase lag between the field that is magnetizing the yokes and the magnetization in the yoke. So you have to look for a material with a small hysteresis loop. And in our case, we have used yokes of mu metal. Okay, this is just for the x-axis. We need it for all the axes. So this is for the z-axis, and now for the y-axis, we should include 2 yokes and 2 coils more symmetrically placed with respect to the sample. The problem is that you need to leave some free room for the aperture of the rheometer to go down and to get access to the sample. So in our configuration, there is only 1 yoke and 1 coil below the sample. So with all those elements, what we look for now, it's for the configuration that returns the largest and most homogeneous magnetic field in the sample area. To do so, we have run three-dimensional finite element method simulations, where we include the whole device and we compute the average of the magnetic field in the sample area and its standard deviation as measurements of the field magnitude and field inhomogeneity. In those simulations, the whole device is included in a computational box, which is large enough to avoid boundary condition effects. All the domains are non-magnetic except for the yokes where we have included the magnetization curve of the new metal. And the last approximation we have done is that we are not going to simulate the coils turn by turn. It is a continuous body where the density, the current density, is adjusted so that it meets the real current density that a bunch of wires will carry. But going back to the geometry, one can find at least 3 parameters to be optimized, and those are the radius of the yoke, the length of the yoke, and the position of the yoke respect to the sample, and again the length, radius, and position of the coils. Those are 6 parameters. The last parameter is the wire diameter that used to do the coils. Ideally, because the Y system is not identical to the horizontal ones, this system is including another 7 parameters, but 14 parameters to optimize 14 parameters was too expensive for us. So what we finally did was we will optimize first the horizontal configuration, and once it is optimum, we will add the vertical one and we optimize it. In order to choose the configuration to be simulated, we follow a brute force approximation. Basically, we take the parameters, we gave them values in a proper interval, and we compute then all the possible combinations with those values. Next, we remove the combination that did not fulfill several requirements. Those requirements are related with the maximum size of the design in order to fit in the rheometer, a safety distance between the moving parts of the rheometer and the generator, the tolerance of the workshop to matching the different pieces. Those 2 properties are related with the symmetry of the horizontal configuration. And the wire diameter, it has another 2 requirements. One is related with the number of turns that has to be large enough to do the approximation of the continuous approximation inside the coil. And the last one is about the maximum current that you are going to apply. That is given, of course, by the maximum voltage of your power source and the resistance of the circuit. And that maximum current has to be smaller than this current, which is this empirical law that returns you the current that a wire can support without burning itself. So after applying all those requirements, they left us with more than 3,000 simulations. We ran them, and those are the results. Here, each point is one of those simulations, because in each simulation we have the field magnitude and the inhomogeneity. We can place them in this chart, and ideally we should look for something in this corner where the magnetic field is maximum and the inhomogeneity is minimum. But you can see that it is not possible with our design. So finally, what we did was compute for each point the ratio between field magnitude and ratio and maximize it. So we will look for a configuration in the red stripe. So repeating exactly the same graph, but now coloring the points according to the input parameters, you can have an idea about what value should have each parameter should have in order to be optimum. So for example, the radius of the yoke should be we should have a value close to the bottom of the range we gave it to it, or for the wire diameter, we should use the largest one we thought. This is just for the XC for the horizontal configuration. We repeat it for the Y configuration. They return 5,000, more than 5,000 simulations. And after running all of them, we got the device. This is the generator, this is the top view, and this is the generator on top of the rheometer. Of course, the dimensions are not exactly the optimum ones due to the tolerances of the workshop. So we repeat the modelization of the generator with the real dimensions in order to calibrate it. And here you can see some results. So finally, the relationship between the magnetic field at the particle position, sorry, at the sample position, and the input current was linear for all the axes. Here is it is shown that the coupling between different axes is not very important. Here, basically, we create a magnetic field that has an angle alpha respect to the x direction. And with a teslameter, we change the orientation of the teslameter, measuring the field. And of course, you only get the total magnetic field when the beta angle meets the alpha angle. On the right, you can see the homogeneity or the magnetic field profiles in the sample area, which is the pink area. So this is the X component of the magnetic field when you move along the X axis from the left yoke to the right yoke. You can see it's not flat, but it's the best homogeneity we were able to get with our device. And this is the Y component of the magnetic field, again, when you move from the left to the right. And of course, it is maximum just when you are on top of the vertical yoke. Here is the same for the when you displace instead of from left to right, when you move from down up, when you move upwards over the yoke, the sample area, which is in that case 1 millimeter. In any of the cases, the points here are experiments, the lines are simulations. You can see a good agreement in all the graphs, so at least we are able to know the magnetic field at each position of the sample area. So now we have the generator. It remains to feed it, to input a current to create the magnetic field. The couple of coils and yokes, they can be represented in a sketch like an inductive term plus a resistive term, element, sorry. And if you plug it to a voltage power source, which creates a steady voltage, you will create a current without problem, and that current will induce the magnetic field, but it will not be a time-dependent magnetic field. If you want a magnetic field that changes in time, for example, using a sinusoidal voltage source, you will have a problem, and it is that although you keep the amplitude of the voltage in the sinusoidal power source constant, if you increase the frequency of that signal, the current you can really create will go down with the frequency. This is a direct result of the Lenz's law. And because of the magnetic field is proportional to the current, the magnetic field is going to go down again. So the most simple solution to avoid this problem is to place or to connect in series with the R and L elements a capacitor, a C element. So in that case, you work with an RLC circuit. In that case, there is a single resonant frequency that depends on the inductance and capacitance of those two terms that allows you to recover the current and the magnetic field and that you were able to create at zero frequency. The problem is that you only have one single frequency. As soon as you move away from this peak, your current will go down. So actually what is placed here is not a single capacitor, but a bank of capacitors connected through switches. How they are connected, you can find it in more detail here in the original reference. And here I will say only that with only 12 capacitors, you can give rise to more than 200,000 different combinations, so more than 200 different capacitances and the related frequencies. In our setup, the state of each switch, open, close, and so on, it's controlled by a PC, so you just input the frequency. With this equation, you know the capacitance you will need. Following this chart, you just move to the combination or to the state of the capacitor bank unit. Here you can see that effectively using the RLC circuit, you can expand the operation range in terms of frequencies of your generator. And this is just for one axis. You need it in triplicate, so that means having 3 fractal banks. Anyway, it's just iterate. The last point I want to highlight here is about the synchronization of the 3 axes. Of course, if you want to work with this kind of magnetic fields, you need the 3 signals to be very well synchronized. For example, here, the total magnetic field is the blue arrow. The horizontal components, X and C, is just the red arrow. And clearly you need that, I'm going to play the, you need a phase lag of 90 degrees between X and C components. But if you are not able to guarantee a constant phase lag, it could happen the following thing. As the operation time of your experiment increases, the magnetic field that you are really creating start to depart a lot from the magnetic field you really want. So one could think that the best way to synchronize everything is to run the 3 power sources with a single clock. The problem is that that is not a good strategy because you are working at resonance. Here you can see the phase lag between the voltage you impose in the power source and the current you create in the circuit. If you work exactly at resonance, the phase lag is going to be 0. So if all the voltages are synchronized, the currents are going to be synchronized. But if for some reason you are not able to work exactly at resonance, there will appear a great phase lag. And those differences could happen just because your capacitor has heat up, so its capacitance has changed, or just because there is a coupling between the yokes of one axis and the other axis. So if changes in L or C are going to move, let's say a little change in L or C is going to create a big move, a big change in the phase lag. So although your voltage is well synchronized, it could happen that the current is not synchronized at all. So to solve that, we have implemented a feedback control loop, where basically we apply a voltage, we measure the current due to that voltage, and then we tune the voltage till the current meets the desired parameters we want. All the details, again, you can find in this reference. And finally, just to show you some preliminary results we have got with the generator, where you can see this is the upper plate of the rheometer moving, and you can see that effectively under shear flow and balanced triaxial fields, the MR or the particles form sheets in the flow vorticity plane, as we have predicted in the simulations. Well, that's all just the conclusions. Magnetorheology in balanced triaxial fields from a computational point of view involve challenges like you have to compute a magnetic force, which is not analytically known, and you will need the iterative method and direct method, in addition to the fact that it is a long-range force. And from an experimental point of view, you will need to design a specific hardware, software. You will have to find a compromise between the magnetic field magnitude and homogeneity, because both things at the same time, we haven't found them. Also, if you want to optimize it, you will have a large number of parameters to play with. And from a rheological point of view, we have seen experimentally and numerically that the particles form sheets, and numerically, we have seen that those sheets do not contribute a lot to the shear stress, while at the beginning of the straining process, it is the pair of particles that are aligned with the extension axis the main responsible ones for the shear stress in the suspension. Yeah, that's all. Thank you for your attention.
Thank you, Jose. That was great and very complete, both simulations and experiments. So that's a very broad talk you've done, and that's great. Questions? Does anybody have questions? Rahul, yeah, please go ahead.
Hi, Jose. Thank
Hi,
you for the
Rahul, how
great
are
talk.
you?
Yeah, I'm fine. Good to see you here.
Yeah.
Hi. So I just have a quick question. So in slide 50, at around 50, you said like the particles that were contributing to the shear stress. So what was the condition for those particles? Like, how did you get the particles which were contributing?
Oh yeah, just here is particles that basically have an individual shear stress above this quantity, 2 × 10⁻⁶.
Okay, got it.
So
Thank
they
you.
are basically the particles contributing positively, because at the beginning of the simulation, we have seen that blue particles are a little quantity, so maybe not very significant, and we focused on the positive ones.
Okay, got it. Thank you.
You're welcome.
And as you are on these slides, just to remember again, maybe I missed it, but can you recall me exactly which interactions between the particles are you taking into account in the simulations? So magnetic, repulsive,
And the Stokes law.
Stokes flow, so short range hydrodynamics.
No
Right.
hydrodynamics, just the Stokes
Oh,
law.
oh, just
primitive
okay,
one.
okay. And what about contacts? Do you also have contacts or not at all?
No, the repulsive force if you want, but
So you
nothing more
prevent
complex.
contact with the repulsive force. That's the point,
Yeah,
right?
yeah,
Okay,
yeah,
okay.
I forgot.
And do you plan to include some hydrodynamics?
Yeah, we plan it. Yeah.
I mean, I guess that in your simulations, you're doing DEM simulations, right?
The discrete element.
Yeah.
Yeah, because Brownian motion is absent. But
so I guess that it would be easy to include at least the short range, because that should be easy
the
to
lubrication,
yeah,
of course.
yeah.
But yeah, I started because I want to learn the stochastic dynamics, full code, not only the lubrications. We started with the whole hydrodynamics forces, and the problem is that if this method is computational expensive, the other one is horrible.
And
Running even with a lot of cores, it doesn't advance a lot.
Because the other problem is that even including lubrication, first you're working at very low volume fractions, that's 10%. So even just that, and also you're forming sheets, so you have long range hydrodynamics between those sheets.
Yeah. And
we could talk about it.
Sure.
you know that's what I do.
Give me hope.
But and so to that, have you started comparing the results you between simulations and experiments?
Not yet, because in terms of experiments, I have more problems.
I can imagine, yeah. But that's incredible. The experimental setup you have.
Well, it's I would say that it was a long time designing it and also building it. Yeah. Of course, I have not done this alone. We need.
But also the
FEM
simulations are great, and they work because what you simulated is exactly what you measure afterwards.
Yeah. I mean, I'm safe in that side of the presentation. At least there is something that agrees. That's what.
Okay. Any more questions?
I just wanted to ask for the experiments, but you didn't study it yet to analyze it, so. But that's
I'll try it. I can say I don't know, and that's all.
Well, you can ask. Questions can always trigger thoughts.
It was mostly about what will you expect the difference between the simulation and the experiments, especially like you have chosen some types of particles, some types of medium, And will you try to change the size of the particles, the concentration, etc., regarding to your simulation? And that can be maybe you will expect something that is not really towards what you expect, like your simulation have done, but I don't know.
Yeah. Well,
Understand.
there will be differences for sure, because for example, in the simulations, we are not including the viscous dissipation from the medium, and in the experiments, we are going to have it. What is more, if the simulations are right and the particle contribution goes down, at the end of the experiment, we will be measuring just the liquid. That will be a difference, of course. And the other difference is I would say, the typical problem we have in Magnetorheology, and it is that you have your sample that is the size is the order of millimeters. Your simulation is the computational box is the size is microns, dozens of microns. So that change in the scale always introduces more differences. Also, the problem, if you say, okay, I will try to change the experimental system, I will use smaller particles or something like that. If you use larger particles, they will go down due to the gravity faster, so that's not good.
You have instabilities with that?
That's something I cannot say, but I guess that a big flock or a big sheet of particle will go down even faster than the particles alone. If you try to increase the viscosity in order to delay that sedimentation, I will need a magnetic field which is much larger in order to induce the aggregation, and that's a problem because the generator cannot create magnetic fields that are so large. So yeah.
Okay, so that's in the future. Thank you.
Yeah, the future.
Is there any more question?
By the way, before stop, I'm going back to the beginning of our conversation. Just for those of you who are looking for a PhD position, can I speak now about this term, or shall I wait? I can't hear you, Michel.
Yes, sorry, I muted myself for. We have you can say it now, but we actually have another question. Are your
right,
particles
sure.
solid, or are your particle rigid or flexible? Soft.
Very rigid. They are made of iron, so as rigid as iron.
Okay.
Actually, I don't know how rigid it is, but it is iron.
It's iron. I would say rigid for these purposes. Okay, thank you. And yes, please go ahead with your with what you wanted to say.
Yes, it's like advertisement, I would say. That recently there has been published a call for a Marie Curie DM, which it's a hub of different universities and companies, and they are looking for 15 PhDs. The universities and companies are at different countries of Europe, but again, I think that everybody can apply for it. Two of the the University of Granada is one of the universities, and another company here in Granada is also in the project, but there are fellows also in other countries of Europe. So if you are looking for a PhD, apply for it if you like gels, colloids, and rheology.
Well, that's great,
You can
Jose.
check everything here.
If you want, I invite you also to send out on our webinar list an email for everybody who's subscribed to our webinar list. It's could be useful, and
Yeah.
that's great. Thank you.
Thank you.
Okay, so you should be able to see my screen now.
Yep.
And so thank you again, Jose. I'm gonna just advertise our next speaker, who's gonna be Duncan Gilbert. It's gonna be in 2 weeks, April 9. He's now a researcher at L'Occitane en Provence, so in industry, and he's gonna talk about particle contact, from particle contact to factory floors, the rough journey of non-Brownian suspensions from theory to application. So he was a PhD student in the same lab and group where I did my PhD. So it's going to be great having him giving a talk. And with that, oh, I have another. Could you please send the link for the fellowship here, Jose? So that's for you. So if
Okay, I
you
will
can
try.
copy paste the link for the fellowship in the chat, that would be great.
I'm going to try, but give me some time because it was
No
a
problem. No.
snapshot.
So people just say here, and I'm gonna stop recording the presentation here. I thank you all for attending our talk today, and see you, well, for all our next talks and classes. And with that, people, you can also stay here for some quick chat. That's what we do usually after the talks. Otherwise, see you soon.